Ever wondered why algorithms hold such a vital place in the realm of computer science? They're the heartbeat of this field, the core that keeps the digital world pulsating. Algorithms are akin to a chef's recipe, a sequence of step-by-step instructions that guide computers to whip up solutions to problems and execute tasks. These coded command sequences are the linchpins that hold the digital universe together. One such influential algorithm in the field of computer science is the Bellman-Ford algorithm. So, have you ever come across the Bellman-Ford algorithm? This is not just any algorithm, it's a graph-searching algorithm that holds a special place in the realm of computer science. It's unique in its ability to calculate the shortest path from a single source vertex to all other vertices in a weighted graph. Imagine you're in a vast city, and you're trying to find the quickest route to all your favorite spots. The Bellman-Ford algorithm is like your personal navigator, efficiently guiding you along the shortest paths. But what makes it truly special is its ability to handle negative weight edges. This means it can even find a quicker route if one was to suddenly appear, even if it's a shortcut that makes your journey shorter by taking you in the opposite direction. Now, you may wonder, how does this algorithm work? Let's dive in. The Bellman-Ford algorithm works in a fascinating way. Let's dive right into the first phase of how this algorithm works. Picture a graph with a bunch of vertices. The algorithm starts by setting the distance from the source to all other vertices as infinite. Why infinite? Well, it's because we have yet to traverse the graph, and so, from our starting point, the other vertices might as well be at the end of the universe. But here's where it gets interesting. The distance to the source itself is set as 0. After all, we're already at the source, so it makes sense that the distance to it is nil, zilch, nada. Now that we have our initial settings, the algorithm begins the process known as relaxing the edges. This is where the magic happens. During edge relaxation, the algorithm traverses the graph, examining each edge one by one. It checks if the distance to a vertex can be shortened by taking a different path. If a shorter path is found, the algorithm updates the distance value, reducing it from infinite to something more tangible. This process of relaxing the edges and updating distances isn't just done once. Oh no, it's repeated for all vertices. The algorithm goes around the graph, relaxing and reducing over and over again, making sure no stone is unturned. This process continues. But what happens next? We left off at the edge relaxation, didn't we? Well, let's pick up right there. After the edge relaxation process, the Bellman-Ford algorithm takes another tour of the graph. And it doesn't just do this once or twice, but n1 times, wherein stands for the number of vertices in our graph. Why n1 times, you ask? It's because the longest path in any graph without a cycle can be n1 edges. So, to ensure we're covering the longest possible path, we need to traverse the graph n1 times. This way, we can be certain that we found the shortest path to every vertex. But what about graphs with negative weight cycles? Here's where the Bellman-Ford algorithm truly shines. After completing the n1 passes, it takes one final journey through the graph. If it can still perform an edge relaxation, it means there's a negative weight cycle present. Why is that? Because an edge relaxation means we've found a shorter path. And if we're still finding shorter paths after n1 traversals, then we must be caught in a cycle that's bringing us back to the same vertex, but at a lower cost each time. In such cases, the algorithm flags the presence of a negative weight cycle and handles it accordingly. So that's how the Bellman-Ford algorithm works, but what are its key points? The Bellman-Ford algorithm is unique in its own way. It's a versatile player in the world of algorithms, capable of handling negative weights, a feat not all algorithms can claim. Not only that, it's got a keen eye for detecting negative cycles, keeping your data clean and clear. And let's not forget its primary mission, calculating the shortest path from one node to all others. Remember, the Bellman-Ford algorithm isn't just an algorithm, it's a tool that has shaped computer science as we know it. Alright, we've come a long way and it's time to wrap things up. But before we do, let's take a moment to appreciate the true power of the Bellman-Ford algorithm. This algorithm is much more than a collection of instructions executed by a computer. It's a testament to human ingenuity, a celebration of problem solving at its finest. The Bellman-Ford algorithm is a pathfinder, and not just in the world of computer science. Think about it. Every time you navigate through a city, every time you solve a complex problem, you're essentially doing what this algorithm does. finding the shortest, most efficient way to get from point A to point B. It's not just numbers and code. It's a philosophy, a way of thinking. It's about optimization and efficiency, about making the most of what we have. So, the next time you're faced with a challenge, remember the Bellman-Ford algorithm. Let it inspire you to find your own path, to make your own way. Because that's what it's all about, isn't it? Not just finding the shortest path, but finding our way. Thank you, Bellman-Ford algorithm, for being a pathfinder, not just in computer science, but in life as well.